Okay, hi everyone. So, another second attempt after the audio didn't work, so try and be as into this as possible. What you've got is for C1 and C2, you've got three types of series or sequences. So let's talk about what I mean by series or sequence. A sequence is when you have a list of numbers separated by commas. So the Fibonacci sequence, for instance, where you're adding up the last two numbers in that sequence. Okay, so a sequence is separated by commas. So this means a sequence of numbers. And a series is when you're adding up the numbers. So if I added them up or subtracted the numbers, okay, uh, and they follow some kind of pattern. There are three types of things you're going to have. So C1 is your recurrence relation, C1 is your arithmetic series, and C2 is your geometric series. Even though C1, the recurrence relation is in C1, it's not until C3 that you actually see the practical point of it. But I'm gonna fast forward that and show you the practical point in this video because I think it's helpful. Um, it eliminates this. Well, what's the point of it? Okay, so arithmetic series is as it sounds. It's when you use arithmetic to move between your terms. So this is term 1, term 2, term 3, and you can see each time we're adding 3 to each number. Whereas geometric series, that's when you are timesing each term. So term 1, 2, 3, 4. I wonder if you can see what's being times every time in order to get the next term. I'll leave you in suspense for that one. So we're going to start off with the recurrence relation. And essentially what the recurrence relation is, it is just a way of coming up with like the way of getting the next term is by using the old term. Okay, so essentially you've got a starting term, x0 is 2. So here you can see that n is 0. So if we want to find x1, that's the same as saying, well, x0 plus 1, that's here. So that's term 1 is your xn, which is x0 minus 5 over 2. So therefore we get x1 is x0, which is 2 from here, minus 5 over 2. And we get 2 minus 5 is minus 3, all over 2. There we go. And then the second term would be using the term before it. So x1 over 2 this time. So x1 we just found out was minus 3 by 2, minus 5 over 2. And then we can start finding that. So in C1 you won't have calculators, but obviously as for speed of the video, I am going to be using them. So let's do a little bit more on this recurrence relation then. So essentially, if you see anything like UK plus 1, UZ plus 1, UN plus 1, something like that, it's going to have something to do with the recurrence relation. And remember, it is a sequence at the moment because you are listing terms, but if we added the terms up, it would be a series. So, the first part says find U1 to U5, and we already have U1 because it tells us that U1 is 7. U2 then will be using the previous term before it, so U1 plus 4, and U1 was 7, so we have 11. Cool. U3 will be U2 plus 4, so 11 plus 4 is 15. Done. U4 will be U3 plus 4, so 15 plus 4, 19. Done. And finally U5, you guessed it, is U4 plus 4, 19 plus 4, so 23. Cool. Now, it says for the next bit, if applicable, find the limit of convergence. So I want to talk about this and what this is essentially meaning, and this will go back to our C3 context. So what is a recurrence relation for, really? Well, it's to find roots of equations that we couldn't otherwise find. What do I mean by that? Well, I'm going to make up a quadratic. That's the quadratic there, right? Um, we want to know where it crosses the x-axis, let's say. And we can do that, can't we? We can factorize this. So x minus 4, x plus 1. So we know it crosses at minus 1 and it crosses at 4. So it looks like that. The thing is, we don't know. Let's pretend that we don't know where it crosses. Okay? We want to know when this, because sorry, we're setting y equal to 0, aren't we? And we're solving when y equals 0. But let's pretend we don't know this. Okay? So pretend don't know. And let's see how we can use a recurrence relation to find those two roots. Now remember, this is C3, but it is good for you to know, oh, that's what you can use it for. Okay, so what I'm going to do is I'm going to start again with x squared minus 3x minus 4 equals 0. And how many roots do we expect there to be? Maximum 2, right? Because we've got x squared. If there was an x cubed, we would expect there to be maximum 3 roots, or x to the 4 maximum 4 roots, yeah? So what I can do is, we can rearrange to make this x equals. So if we go x squared equals, bring in the 3x over and the 4 over, and then square rooting, can you see x equals that, right? If I put an n plus 1 and an n in there, this looks exactly like a recurrence relation now, doesn't it? This is what's called an iteration formula. Okay? But what we need is a starting value to make this work. So how about I pick a starting value? Let's go for, say, so let's say x1 was minus a half. So, and what I'm going to try and do is, I'm going to put this in my calculator. So I've got x2 then. So my second approximation for the root is 3. Because at the moment, this is my first approximation. I reckon the root's minus a half. And let's see if it is minus a half. Because if it is minus a half, when I make x2 my second approximation for the root, I should get minus a half again. But if you whack this in your calculator, so if you do your answer button trick, so if you put minus a half equals, do this at the same time and you'll see 3 answer plus 4 rooted, you get root 10 over 2. If you just press equals again, you get 2.956926866. Do this with me, yeah? Do this with me. Keep pressing equals, 3.94, 3.97, keep pressing equals, keep pressing equals, keep pressing equals. And you'll see it's converging, isn't it? It's converging 3.999999 until it hits 4, 4, 4, 4. So you get, in the end, xn is 4. You see it's converged to the root, and it's found a root for you. Wow. How does that work? C3. We'll talk about that in C3. So, that was just for interest. That's what the recurrence relation is for, where it's used for. But let's just finish this bit here, which says, if applicable, find the limit of convergence of this thing then. Okay? Essentially what happened in that example I just did with you, the C3 example, it converged to the number 4, didn't it? All the numbers came together at the number 4. So every single term, if I pressed equals an infinite number of times, I would just keep getting 4, 4, 4, 4, 4, 4, right? So when it says, is this thing converging to a number, well, we can test it, because essentially that un plus 1 means your last term, doesn't it? If n tends to infinity, un plus 1 is your last term, so I'm going to call that L, or the limit of convergence. The term just before it is un, isn't it? Now if we're going to infinity, just like before in my calculator, the millionth term was 4, and the 999,000 for 999th term was 4. So they would be the same. Can you see? Now if this thing does, so that's my plus 4 at the end, if this thing does converge to a limit, then I should get a reasonable equation to get L equals. But you can see L and L cancel, and I get 0 equals 4, which means this thing diverges. It means it diverges. And it's obvious it's going to diverge, isn't it? Because every time I'm adding 4. And if you keep adding 4, it's just going to tend to infinity. It's not going to tend to a single number if I keep pressing equals. Let's try this second one then. Add in the always escalating in the difficulty. That should be okay there. So if I've got UK plus 1 is UK minus 2 over 3, where U1 is 4. Okay, it says here, find sigma UK, where K varies from 1 to 4. Now what does this sigma mean here? So to the side, this is sigma, which is Greek for sum. So it means find the sum as K varies from 1 to 4. And this is what's called the countable sum. You'll notice when we do integration, we'll be using the uncountable sum, which is that elongated s here with a dx on the side. Okay? But for now, countable sum means going up in integers, so whole numbers, from k varying from 1, 2, 3, all the way up to 4. So this means it's a series, doesn't it? Because we're summing all of our terms. So let me show you what I mean by this. So u, k, where k varies from 1, so u1 plus, all the way up to u4. You see? So I need to find term 1, term 2, term 3, term 4, and then add it together using my recurrence relation. So let's do that. So u1 we know is 4 already, so that's 4. u2 is the previous term over 3. So 4 minus 2 over 3 is 2/3. u3 is the previous term over 3. So 2/3 minus 2 over 3, which is minus 4 over 9. So minus 4 over 9. And u4 finally is u3, take 2 over 3. So minus 4 over 9, minus 2 divided by 3. So minus 22 over 27, minus 22 over 27. Now if I add them all together, hopefully you're doing this too, I get 92 over 27, okay? Done. And again, it's asking us to find the limit of convergence of this thing. So if I kept finding new terms, u5, u6, u7, u a million, will this converge to a single number? Well, like we said, remember the last term, the infinitely many term on, we call that L. The previous term before that's still going to be L. And then we'll see if we can come up with an equation for L. Well, if we times both sides by 3, bring the L over, I get L equals minus 1, i.e. this thing will converge to minus 1. You can test this in your calculator now. Let's do that answer button trick again. So if you press 4 equals, because your first term is 4, and then you put that into your UK minus 2, so answer minus 2 divided by 3, press equals, you get your 2/3. Press equals, you get minus 4 by 9, press equals, minus 22 over 27. Just keep pressing equals, loads and loads and loads of times, and it will converge on your calculator to minus 1 every time. I really hope you're testing that. Okay? And that's it for recurrence relation.